Hello and welcome. In this video, we will explore the relationships between lines in 2 and 3 dimensions, a key topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to classify pairs of lines as intersecting, parallel, coincident, or skew. You will also learn how to find the point of intersection for lines that meet, and how to calculate the shortest distance between skew lines. We'll begin by examining lines in a two-dimensional plane. In this setting, there are 3 possible relationships between any 2 distinct lines. First, the lines can be intersecting. This means they cross at exactly one point, giving us a unique solution to their equations. Second, the lines can be parallel. They run side by side, never meeting. Algebraically, this corresponds to a system of equations with no solution. Third, the lines can be coincident. This is the case where the 2 equations actually represent the exact same line. As a result, every point on the line is an intersection point, leading to infinitely many solutions. To determine which of these relationships holds for a given pair of lines, we can use a powerful technique called row reduction on an augmented matrix. Let's see how this works with an example. Let's work through an example to find the intersection point of 2 lines. Our goal here is to solve a system of linear equations using row reduction. Consider the system of equations 3x plus 5y equals 9 and 2x minus 3y equals negative 13. First, we'll write this system as an augmented matrix. The first column will contain the coefficients of x, the second column the coefficients of y, and the third column the constants. This gives us the matrix with rows 3, 5, 9, and 2, minus 3, minus 13. Our objective is to transform this matrix into row echelon form, which means we want a 1 in the top left corner and a 0 below it. Let's start by getting a 1 in the first position. We can achieve this by multiplying the first row by 1/3. This operation is written as 1/3 R1 goes to R1. Next, we need a 0 in the second row, first column. We can do this by subtracting 2 times the new first row from the second row. The operation is R2 minus 2 times R1 goes to R2. Let's calculate this. 2 times the first row is 2 10/3, 6. Subtracting this from the second row, 2 minus 3 minus 13, gives us 0 minus 19/3 minus 19. So our matrix becomes 1, 5/3, 3, and 0, minus 19/3, minus 19. We're almost there. Let's simplify the second row by getting a 1 in the second position. We can multiply the second row by negative 3/19. This gives us 0, 1, 3. This matrix is now in row echelon form. We can convert it back into a system of equations. The second row, 0, 1, 3, translates to 0x plus 1y equals 3, which simplifies to y equals 3. The first row, 1, 5/3, 3, translates to x plus 5/3 y equals 3. Now we can use back substitution to find x. Substitute y equals 3 into the first equation. X plus 5/3 times 3 equals 3. This simplifies to x plus 5 equals 3, which means x equals negative 2. Therefore, the lines intersect at the point with coordinates negative 2, 3. This is a unique solution, confirming that the lines are intersecting. Now, let's explore the other 2 possibilities, parallel and coincident lines. We'll use another example involving a constant, which is a common feature in IB problems. Consider the system x plus 3y equals 5 and 4x plus 12y equals k, where k is a constant. We want to find the geometric interpretation of the solutions. As before, we'll start by writing the augmented matrix. The matrix is 1, 3, 5, and 4, 12, k. The first row already has a 1 in the first position, so we can proceed to eliminate the 4 in the second row. We'll perform the operation r2 minus 4 times r1 goes to r2. 4 times the first row is 4, 12, 20. Subtracting this from the second row, 4, 12, k gives us 0, 0, k minus 20. Our reduced matrix is 1, 3, 5, and 0, 0, k minus 20. The second row is the key to understanding the relationship between the lines. The second row represents the equation 0x plus 0y equals k minus 20. This simplifies to 0 equals k minus 20. We must consider two cases. Case 1. If k is not equal to 20, then k minus 20 is a non-zero number. The equation becomes 0 equals a non-zero number, which is a contradiction. This means there are no solutions to the system. Geometrically, no solutions means the lines are parallel. They have the same direction but are distinct. Case 2. If k is equal to 20, then k minus 20 is 0. The equation becomes 0 equals 0, which is always true. This means the second equation is redundant and provides no new information. Geometrically, this means the lines are coincident. They are the same line. We can find the solutions from the first equation, x plus 3, y equals 5. We can express the solution parametrically. Let y equal t, where t is any real number. Then x equals 5 minus 3t. So the solutions are of the form 5 minus 3t, common t. Now, let's extend our analysis to 3 dimensions. In 3D space, the relationships between lines are more complex. We still have parallel, intersecting, and coincident lines, but there's a new possibility. This new relationship is called skew. Skew lines are lines that are not parallel and do not intersect. Imagine two lines on opposite walls of a room that are not parallel to each other. They will never meet. To classify lines in 3D, we follow a two-step process. First, we check for parallelism. Second, if they are not parallel, we check for intersection. Step 1. Check for parallelism. Two lines are parallel if their direction vectors are scalar multiples of each other. If they are parallel, we then check if they share a common point. If they do, they are coincident. If not, they are parallel and distinct. Step 2. If the lines are not parallel, we check for intersection. We do this by setting their parametric equations equal to each other. This will give us a system of 3 equations with 2 unknowns. If this system has a unique solution for the parameters, the lines intersect. If it has no solution, the lines are skew. Let's apply this process to an example. Consider line 1 with direction vector v equals 2, minus 2, 4, and line 2 with direction vector w equals minus 1, 1, minus 2. Step 1. Check for parallelism. We can see that the direction vector of line 1, 2, minus 2, 4 is equal to negative 2 times the direction vector of line 2, minus 1, 1, minus 2. Since 1 is a scalar multiple of the other, the lines are parallel. Now we must check if they are coincident. We can do this by picking a point on one line and seeing if it lies on the other. Let's take the point on line 1, when the parameter s is 0. This gives us the point P, 1 at minus 1, 1, 1. Now we'll substitute this point into the equation for line 2. This gives us 3 equations. Minus 1 equals 1 minus t, 1 equals t, and 1 equals 3 minus 2t. The second equation immediately tells us that t must be 1. Let's check if this value works for the other 2 equations. For the first, minus 1 equals 1 minus 1, which is 0. This is false. For the third, 1 equals 3 minus 2 times 1, which is 1. This is true. Since t equals 1 does not satisfy all 3 equations, the point P1 is not on line 2. Because the lines are parallel but do not share a common point, we conclude that they are parallel and distinct. Let's continue with another example from the same set of lines. This time, we'll investigate the relationship between line 2 and line 3. Line 2 has direction vector w equals minus 1, 1 minus 2, and line 3 has direction vector u equals 2, minus 1, 3. Step 1. Check for parallelism. We compare the direction vectors w and u. Is minus 1, 1, minus 2 a scalar multiple of 2 minus 1, 3? No, it's not. For example, the first components would require a scalar of minus 1/2. But this doesn't work for the second components, so the lines are not parallel. Step 2. Check for intersection. We set the parametric equations equal to each other. Equating the x, y, and z components gives us a system of three equations. 1 minus t equals 1 plus 2u, t equals minus 1 minus u, and 3 minus 2t equals 4 plus 3u. We can solve this system. Let's use substitution. Substitute equation 2 into equation 1. Substituting t equals minus 1 minus u into the first equation gives 1 minus 1 minus u equals 1 plus 2u. This simplifies to 2 plus u equals 1 plus 2u, which means u equals 1. Now that we have u equals 1, we can find t using equation 2. T equals minus 1, so t equals minus 2. We have found values for t and u. The crucial step is to check if these values satisfy the third equation, which we haven't used yet. Substitute t equals minus 2 and u equals 1 into equation 3. 3 minus 2 times minus 2 equals 4 plus 3 times 1. This gives 3 plus 4 equals 4 plus 3, which is 7 equals 7. The equation holds true. Since we found a consistent solution for t and u, the lines intersect. To find the point of intersection, we can substitute u equals 1 into the equation for line 3. This gives us the point. 3 minus 2, 7. We could also substitute t equals minus 2 into the equation for line 2, and would get the same result. The problem also asks for the angle between the lines. We can find this using the scalar product formula. The cosine of the angle theta is the absolute value of the scalar product of the direction vectors divided by the product of their magnitudes. This gives us 9 divided by the square root of 84. Calculating this, we find that the angle theta is approximately 10.9 degrees. Let's look at one more 3D example to see what happens when lines are skew. We'll use line 1 and line 3 from our previous set. Line 1 has direction vector v equals 2 minus 2, 4, and line 3 has direction vector u equals 2 minus 1, 3. Step 1. Check for parallelism. We compare the direction vectors v and u. Is 2 minus 2, 4, a scalar multiple of 2 minus 1, 3? No. The first components would require a scalar of 1, but this doesn't work for the second components. So the lines are not parallel. Step 2. Check for intersection. We set the parametric equations equal to each other. Equating the components gives us the system. Minus 1 plus 2's equals 1 plus 2u, 1 minus 2's equals minus 1 minus u, and 1 plus 4's equals 4 plus 3u. Let's try to solve this system. A good strategy is to add equations 1 and 2. Adding the left sides gives minus 1 plus 2's plus 1 minus 2's, which is 0. Adding the right sides gives 1 plus 2u plus minus 1 minus u, which is u. So we find that u equals 0. Now that we have u equals 0, we can substitute it back into equation 2 to find s. 1 minus 2's equals minus 1 minus 0, which means 1 minus 2's equals minus 1. Solving for s gives s equals 1. We have found values for s and u. As before, we must check these values in the third equation, which we haven't used yet. Substitute s equals 1 and u equals 0 into equation 3. 1 plus 4 times 1 equals 4 plus 3 times 0. This gives 5 equals 4. This is a contradiction. Since the system of equations is inconsistent, there is no solution. This means the lines do not intersect. Because they are not parallel and do not intersect, we conclude that the lines are skew. We've seen how to classify lines. Now let's tackle a more advanced problem, finding the shortest distance between two skew lines. This is a classic IBHL question. The key idea is that the shortest distance between two skew lines is the length of a line segment that is perpendicular to both of them. Let's call the direction vectors of our two lines v and w. The direction of this shortest distance vector, which we'll call AB, must be perpendicular to both v and w. The only vector that is perpendicular to two given vectors is their cross product. So the vector AB must be parallel to the cross product of v and w. This gives us a powerful method. Let's apply it to an example. Find the shortest distance between the lines L1 and L2. L1 has direction vector v equals 1, minus 1, 1, and L2 has direction vector w equals minus 1, 2, minus 1. Step 1. Find the cross product of the direction vectors. The cross product v cross w is calculated as the determinant of a matrix. This gives us the vector minus 1, 0, 1. This vector is perpendicular to both lines. Step 2. Express the vector AB in terms of the parameters t and s. A general point on L1 is t, 1t, 2 plus t. A general point on L2 is 3s, minus 1 plus 2's 4s. The vector AB is the position vector of B minus the position vector of A. This gives us the vector 3st minus 2 plus 2's plus t, 2st. Step 3. Use the condition that AB is parallel to V cross W. This means AB must be a scalar multiple of minus 1, 0, 1. Let's call the scalar k. This gives us a system of three equations. Step 4. Solve the system for s and t. Notice that the right sides of equations 1 and 3 are opposites. If we add the two equations, we get 5 minus 2's minus 2t equals 0. From equation 2, we can rearrange to get t equals 2 minus 2's. Substituting this into our new equation gives 5 minus 2's minus 2 times 2 minus 2's equals 0. This simplifies to 1 plus 2's equals 0, so s equals minus 1/2. Substituting s back into the equation for t gives t equals 3. Step 5. Find the vector AB and its magnitude. Now we substitute s equals minus 1/2 and t equals 3 back into our expression for AB. This gives us the vector 1/2, 0, minus 1/2. The shortest distance is the magnitude of this vector. The magnitude is the square root of 1/2 squared plus minus 1/2 squared, which simplifies to 1 over the square root of 2, or root 2 over 2 units. Let's recap what we've covered. We started by classifying lines in 2D as intersecting, parallel, or coincident, using row reduction. We then extended this to 3D, introducing the concept of skew lines. We learned a two-step process to classify 3D lines. First check for parallelism, then check for intersection. Finally, we developed a method to find the shortest distance between two skew lines. This involved finding a vector perpendicular to both lines using the cross product, and then solving a system of equations to find the specific points that define the shortest distance. These are fundamental concepts for vector applications in IB mathematics. Now, let's test your understanding with some practice questions. Here are 5 practice questions designed to reflect the style and difficulty of IBHL assessments. Pause the video and try to solve them on your own. The solutions will follow. Question 1. Classify the lines x equals 1 plus 2t, y equals 2 minus t, z equals 3 plus t, and x equals minus 2 plus 3's, y equals 3 minus s, z equals 1 plus 2's. If they intersect, find the point of intersection and the acute angle between them. Question 2. Consider the system of equations 2x plus 3, y equals 5, and 4x plus 6y equals k. For what value of k are the lines coincident? For what values of k are they parallel and distinct? Question 3. Find the shortest distance between the skew lines r equals 1, 0, 2 plus t times 2, 1 minus 1, and r equals 0, 1, 1 plus s times 1 minus 1, 3. Question 4. The lines L1 and L2 are given by r equals 1, 2, 3 plus t times a, 1, 2, and r equals 0, 1, 1 plus s times 1, 2, 3. Given that the lines intersect, find the value of the constant a. Question 5. A triangle ABC is formed by the lines AB, AC, and BC. The vector equations are given. Find the coordinates of the vertices A, B, and C. Welcome back. Let's go through the solutions to the practice questions. Question 1 asks us to classify two lines and find their intersection if it exists. First, check for parallelism. The direction vectors are 2, -1, 1, and 3, -1, 2. They are not scalar multiples, so the lines are not parallel. Next, check for intersection. Equating the components gives us a system of 3 equations. Solving the first 2 equations gives t equals 1 and s equals 1. Substituting these into the third equation gives 4 equals 3, which is false. This is a contradiction, so the lines do not intersect. Since the lines are not parallel and do not intersect, they are skew. Question 2 involves a system with a constant k. We form the augmented matrix and perform the row operation R2 minus 2 times R1. This gives us the matrix 2, 3, 5, and 0, 0, k minus 10. For the lines to be coincident, the second row must be all zeros. This means k minus 10 must equal 0, so k equals 10. For the lines to be parallel and distinct, the second row must be 0, 0, non-zero. This means k minus 10 must not equal 0, so k can be any real number except 10. Question 3 asks for the shortest distance between 2 skew lines. First, find the cross product of the direction vectors 2, 1, minus 1, and 1, minus 1, 3. The result is 2, minus 7, minus 3. Next, express the vector AB in terms of t and s. This gives us minus 1 minus 2, t plus s, 1 t dash s, minus 1 plus t3s. Set A, b equal to k, times the cross product. This gives a system of 3 equations. Solving this system yields t equals 1/2 and s equals 1/2. Substitute these values back into the expression for a, b to get the vector minus 1, 0, minus 2. The shortest distance is the magnitude of this vector, which is the square root of 5 units. Question 4 gives us 2 lines that are known to intersect and asks for a missing constant. Since the lines intersect, there must be a solution to the system of equations formed by equating their components. This gives us 3 equations. We can solve the second and third equations for t and s. From the second, s equals 1 plus t slash 2. Substitute this into the third equation to find t equals 1. Then s equals 1. Now we use the first equation, which contains the constant, a. Substitute t equals minus 1, and s equals 0. This gives 1 plus a times minus 1 equals 0, which simplifies to 1 minus a equals 0. Therefore, a must be 1. Finally, question 5 asks for the vertices of a triangle formed by 3 lines. Each vertex is the intersection of 2 of the lines. We need to solve 3 systems of equations. Vertex A is the intersection of lines A, B, and AC. Equating their components gives a system of 2 equations. Solving this system gives r equals 1 and s equals 2. Substituting s equals 2 into the equation for AC gives the point A at 2, 4. Vertex B is the intersection of lines A, B, and BC. Equating their components gives another system. Solving this system gives r equals 3 and t equals minus 1. Substituting r equals 3 into the equation for AB gives the point B at 8, 0. Vertex C is the intersection of lines AC and BC. Equating their components gives the final system. Solving the system gives s equals 5 and t equals minus 5. Substituting s equals 5 into the equation for AC gives the point C at 5, 7. So the vertices of the triangle are A at 2, 4, B at 8, 0, and C at 5, 7. That concludes our session on the relationships between lines. We've covered the essential concepts and problem-solving techniques required for the IBAAHL curriculum. Remember to practice these methods, especially the row reduction for 2D lines, the two-step classification for 3D lines, and the cross-product method for finding the shortest distance between skew lines. Thank you for watching.